Now we're recording.
Hi, Lucas.
They all wanted to say hello.
Hey, Lukey Pookie.
Wow.
That's what I call Luke.
Lucas.
Lucas Pookus.
Well, we're going to go on, and he's not going to listen to us just say hello for the next 35 minutes. All right, we are going to continue lesson 2. But we had homework last night. It's okay. We'll talk about that later. Okay, so put your homework away. We'll get it out in a little bit. We're going to move on with lesson 2 before we do anything else. So lesson 2, I believe we got to talk about congruent statements. Tick marks. Did we talk about tick marks?
Yes.
Yes, we did. And congruency statements. So you got your notes out. I am on page 7 if you would like to follow along. Congruency statements, we will have properties, congruency properties. Okay? These in a box on the bottom of page 7. It's good to know these properties. Do I need to write them down? Most definitely you do. Okay? The reflexive property. Do I have to write out property of congruency? I don't. I'm going to write P-R-O-P. Reflexive property. The reflexive property is, in geometry, segment AB is congruent to segment AB. Whoa. That's deep right there. This line segment is congruent to itself. Okay? These seem kind of basic. This is the most fundamental, the one we will use most often, and you will forget about it more frequently than not. The reflexive property of congruency is AB is congruent to AB. The next one is the symmetric property. It says, well, if AB is congruent to CD. Now there's another segment in there, it's not just itself. If AB is congruent to CD, then CD is also congruent to AB. Here's one more. The transitive property. I remember the transitive property because it seems like it's the longest. It's as long as a train. Okay, so it's going to be the longest of all 3. They get a little bit more complicated. They add a step each time. The transitive property says, if AB is congruent to CD and CD is congruent to EF, then guess what? AB is congruent to EF. So these 2 middle pieces must be the same to connect. Okay? If I was saying this in algebra class, the reflexive property would look like A equals A or X equals X. Okay? Something you know. Symmetric property is going to look like A equals B, B equals A. Okay? The last one, if A equals B and B equals C, then A equals C. We're in geometry and we're going to talk about line segments. Okay? Because I believe this was lesson 2, segments. Are we okay with all of these properties? We're going to go on. From these properties, we can use them. You will have to identify them. We're going to talk about a postulate. I know the first day we read the definition of a postulate. We're going to read it or write it again. What is a postulate? just in case you don't remember what it said the other day, from day one, it's in your book. It's a blue word. Go ahead, Paxton.
Statement that is accepted as true without proof.
Statement accepted as true. We are happy these postulates are accepted as true. We never have to prove this postulate we're fixing to talk about. I forgot to plug my computer at that lunch. Okay? So we're going to read postulate 1. We're not going to write it down right now. Okay? We're just going to read it. So I'm on page 8. Can someone read postulate 1 for me? Go ahead, John.
Okay. Points on a line compared to a 1-to-1 correspondent with a real number such that any two given points can have the coordinates 0 and 1, and the distance between 2 points is the absolute value of the difference of their coordinates.
Okay, there's a lot of words. Let's start with the beginning. The first 4 or 5 letters, 4 or 5 words. What does that say? The points on a line. Does everybody envision now a line? How many points are on that line? There's an infinite amount of points on this line. Okay? Then let's go on. So an infinite amount of points on a line can be paired in a 1-to-1 correspondence. So here's 1 point, here's another point. With the real numbers. What are real numbers? 1 is a real number. 2?
Isn't 1 through 1 to all positives possible?
Okay, so here's what I'm hearing. 1, 2, 3, etc., etc., etc. What do we call those? Is that all the real numbers? I just put in a set. A set of numbers. 1, 2, 3, 4, 5, 6, etc., etc., etc. What is that set of numbers called? Not in this book. It's very much of an Algebra 1 day, 1 lesson, 1 question. First lesson in Algebra 2.
Oh, integer.
1, 2, 3, 4, 5. What am I doing? Counting. Are these the
Oh,
counting numbers? Alright, they are also, how are we going to spell that? Counting numbers are also called natural numbers. You need to know that. Okay? Counting numbers and natural numbers. So we're having a little bit of an algebra review right now. Before we can unpack this postulate, we need to know what all the words in the postulate are meaning. Okay? If I want to go a step further and add something to this set of numbers that I have, the counting numbers, what would I go to next? The negatives. What negatives? The counting numbers opposites? Okay, so that would be what? -3, -2, -1, but these dot, 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 so that way technically. Plus these, what are those called? No. No, she already tried that. What?
Negative integer.
I like the word integers. I don't like the word negative. Integers. What are integers? Oh no.
Any number.
What? What did you say? What are whole numbers? We haven't put up whole numbers. We put up counting numbers. And now you've added in this piece these integer things that have the opposites of all the counting numbers. What number do we not have up there? 0. Do you know where 0 goes? them, what do we call them? Whole numbers. What are whole numbers?
Any number that's not decimal.
All the counting numbers plus 0. Okay, so question in a pre-algebra book says, what number is a whole number that's not a counting number? 0. Okay, so counting numbers are the numbers you can actually count with. Whole numbers include 0. Integers include all of that plus the negatives. So really, the definition of integers is the counting numbers, their opposites, and 0. Okay? What's next? What goes above that? Like the half stuff. What's it called? Okay, like the fractions. What is it called? Okay, like the decimals. What's it called? You've given me some decimals, some fractions. These are just examples. What's it called? Starts with an R.
Rational numbers.
Rational numbers. Why? Because a fraction is a what? Ratio. Ratio. If you want to talk about root words, ratio. So rational numbers are fractions or ratios of integers. Okay? As long as these fractions will repeat or end, it is going to be a rational number. Does that make sense? So if there are rational numbers, what else do we have out there? Irrational numbers. What is an well? Can you be a rational number and an irrational number at the same time? You can? So what did I just say about rational numbers?
No, you can't.
They're
Yep.
fractions that will either end, 1/2 is 0.5. 1/3 is 0.3 repeating. So it's going to repeat or it's going to end. What's special or not special, I don't know, about irrational numbers?
They're like, they have a bigger number on top than on bottom. No?
9/4. That's 2 1/4. That's 2.25. That decimal ended. What's special about pi? It goes on forever and ever. The decimal will never end, and it will never repeat.
Okay. So how does that even work? I've always kind of been confused about a pi number.
What the pi number is? Well, the fun thing is, what do you know about pi? Other than you want to eat it.
It helps to find like circumference.
I'm going to tell you a little secret. That's not how that came up. Okay? Does everybody see something that's circle? Let's find something that's circle. Okay? There's a circle. Where did they come up with pi? They could actually measure the distance around the circle, which is the what? Circumference. So they could find the circumference. Then they could actually measure the distance across. What's the distance across?
Diameter.
The diameter. They took circles, medium size, small size, really big size, and took circles of every size. And they measured the distance around and the distance across. And guess what they did? They made a ratio. Okay? So they took two numbers and they divided the circumference. This is a very side note. The circumference divided by the diameter. And what did they get? Every time. 3.14159, etc., 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 depending on how far out they took the division. Depending on how accurate they were in their measurements. Okay? So, they found out that there's this very special number, and the decimal never ends. Who's got tiny handwriting? Lots of you probably do. If we started in the corner and we started writing and we went all the way around the board, all the way around the walls, we would write all the way, little bit of handwriting, all the way to the bottom. We still wouldn't be able to do the rest. It's going on forever, ever, ever. Okay? So, they came up with this before you had C equals pi d. Okay? So, we have an approximation for pi. We have a couple approximations for pi. What's one? 3.14. Somebody try to tell me that that's pi. Listen, no, it's not. It's not. It's an approximation for pi. 22 divided by 7 is an approximation for pi. Okay, it comes out to 3.14, but it's a 2 something. Okay? 22 over 7 is a rational number. It's an integer divided by an integer. 3.14 is a rational number. It's a decimal that we've stopped. Okay? Pi is not. Okay? Was that somewhat good description? More than you probably needed or wanted? Okay? Are there any other irrational numbers? There has to be. There's lots of them. Things that you don't know. Tell me. What's the square root of 2? What times itself is 2? No idea. I'll give you an approximation for it. It's 1.41. That's an approximation. Okay? Because I've rounded it. Guess what? If I put it in my calculator, it's going to give me 10 digits. If I just keep going, if I said no, there's no restriction, it's going to give me an infinite number of decimals. Never going to repeat, never going to end. So what about the square root of 3? Do you know the square root of 3? No, you don't. It's approximately 1.73. I just have numbers in my head. I don't know why. If I keep going, I don't know anymore. Square root of 7. Square root of 11. Square root of 72. Do you know any of those?
Oh, yeah.
No.
Wait, so, like, no, never mind.
It's okay. Any square root that you don't know. So if it's not a perfect square, then that number is an irrational number.
I was going to say prime numbers, nevertheless, that's completely different.
It's completely different. Yeah. Yes, the small prime numbers, but then 72, you don't know the square root of 72. Or 12. Right? The only squares you know are the 1, 4, 9, 16. How did I go back to the 3rd or 4th grade where you learned that song? Right? Perfect squares are so much fun. Yay. Okay. What's next? We still haven't gotten to our question. What was our original question? Have we even got to number 1 of our postulates? No, what are we on? What are we trying to do? What's the whole point of this whole thing? We already talked about points. It's on a line. Something with the real numbers. We're trying to define real numbers. We're just trying to know the definition of all the things that's in this postulate. So, can we group irrational together with rational? Can we put something that combines them all? You better have seen it. You need to shake your head and tell me you've seen this. Okay, whether it's true or not, you need to have seen this. Please tell me you've seen it. Something puts a box around the whole thing, and they are called real numbers. All irrational and rational numbers are called real numbers. Alright, so now we have a concept of what we're talking about. Anybody have anything you want to comment on?
So it's basically just every number.
Thank you so much, Paxton, for saying that. Just so I can say, absolutely not. Okay? It's like all numbers. It's every number. Except the ones that aren't. What? Say what?
Why is it around the whole thing?
So, was everything under rational numbers? No. There were some that were over on the side that were irrational. Okay? You don't know right now, but eventually you're going to find out that not everything is a real number. Algebra 2, I hope you saw it. Okay. You learn about some things that are not real numbers. Okay? Because I had one of my new kids in another class go, well, what about I? Wait, we're not going there. If you're a freshman, you don't know. You don't know anything other than this. Okay? But I'm not going to make you believe that there's nothing else out there. Okay? We want to believe there's more out there. Okay? Real numbers are all rational numbers and irrational numbers. Okay? You will learn in Algebra 2. You're going to do this exact same thing in Algebra 2. First week. Remember this. Got it? Promise me that you'll remember this for Algebra 2. Yes. Miss Evans, I promise I will. Okay? Yes. So, when we're talking about real numbers, can I now put pi on a number line? Yes, I can on this one. It tells me the ruler postulate says I can put any real number on this number line. That pulls in integers. Usually, when you're thinking of a number line, you're thinking of integers. All the negatives, 0, and the positives, right? This is telling me I can put fractions, I can put irrational numbers, I can put anything I want that's a real number on the number line. Okay? Excuse me. So, now here we go. Let's finish reading. I have a number line somewhere. Here we go. It says something about in correspondence so they can have a value of 0 and 1. A pair. I pick a pair of points on this line. They can be anywhere. They can be close to each other. They can be far away from each other. And they can have the values of 0 and 1. They can have the values of 3 and 4. They can have the values of anything, and I can put them that unit away. Not the most important postulate part that we're going to use. Number 2 is much more important. It says, talking about the what?
Absolute value.
Keep going.
Distance between 2 points.
The distance between 2 points. So I can find the distance between 2 points that are on this number line. What's the distance between 0 and 1? 1. Okay, that's not very crazy. But what if I was crazy? Oh, I made my eraser really small. What if I put pi and pi plus 2? Could I do that? What's the distance between pi and pi plus 2? 2. Okay, it's not a trick question. So I can put anything I want now on this number line. Okay, so I'm going to actually put some numbers. I'm going to put some integers because that's what we like. So I'm going to go, if that's still 0 and 1, negative 1, negative 2, 4. That was not 5. That was 4. But I want to be at 5. Can I find the distance? What is distance? Do we need to define distance before I do this? I think I have. What does it mean? Paxton was trying to read something. What is the distance? You can read the blue word if you want. Go ahead, Sadie.
Distance is the measure of the segment connecting two
the measure of the segment connecting 2 points. Below that, I think it says something even more important. That distance cannot ever be negative. Distance cannot be negative. You need to know that. If I'm standing right here and I walk, take 5 steps, I've covered a set distance. This time I'm going to walk backwards. Because I'm walking backwards, I'm covering negative distance. No. It's the exact same distance that I've traveled, whether you're going in reverse or in forward. Okay? Didn't work in Ferris Bueller's Day Off. He put his car in reverse and tried to take the miles off his car. It did not work for him. So it cannot be negative. It's not coming off. Okay? Also, in the postulate, it did talk about the absolute value. The distance is the absolute value of the coordinates. The difference of the coordinates. So if I want to define the distance from -2 to 5, can I write an equation for that? Sure. What would it look like? I'm going to say it's absolute value of the coordinates difference. What does difference mean? Subtraction. So I'm going to say -2 minus 5. How do you do that? Okay, so I'm going to add the opposite, right? Every subtraction I'm going to add the opposite, and I'll get what? Absolute value of -7, which is +7. Okay? What? But I didn't read, somebody else didn't read the coordinates like that. They saw 5 minus -2. What's 5 minus -2? You're going to add the opposite. Absolute value of 7 is 7. You get the same answer either way you do it because of those absolute values. Not everybody likes to write formulas. Some people literally just want to, if it's on a straight line, this will always work. Start at 1. 1, 2, 3, 4, 5, 6, 7. You can actually do the bunny hop all the way there. You get the same number. Okay? Don't forget that. If you're on the same line, just count the units till you get there. You don't always have to put it in the formula. Okay? All right. Moving on. We're not going to talk about all of everything because I feel like you can do this. Next postulate we get to, we're going to read. Joanna, will you read postulate 2?
If B is between A and C, then AB plus BC equals AC.
And what's the name of that?
Segment addition postulate.
Segment addition postulate. I'm not going to use A, B, and C if that's okay. I'm going to put W, Y, and Z. And I know that's not alphabetical perfect, and it's okay. So Y is between W and Z. Can somebody name a segment that's up here? Thumbs up. You can name a segment. John, give me a segment.
Is it W1?
WY is a segment. Paxton, is there another one?
W to Z.
W to Z. Is there another one? It's 80. Y to Z. We can say all of those with reverse letters, and they're the same. Okay, those are all count. But there are 3 different segments. There's a little shorter segment, and there's a longer segment, and then there's the total. And the segment addition postulate says this piece plus this piece equals the total piece. Okay? If you don't write this postulate down in your notes. Okay? I know one of my classes, they wanted to write down their notes. So look, you're going to have to put it on a separate piece of paper for later. If you don't want to write it twice, don't write it now in your notes. Does that make sense? Okay. So I just want to to work with them and then we'll go write them later. Okay? What if I tell you WY equals 7 inches and WZ equals 32 inches? What is Y to Z? Okay, before we do math, did I do anything wrong? There's something up there that I wrote down that you don't like. Really? Thank you for asking. Because sometimes I can make mistakes. Do the segments WY, you told me that was a segment, right? Does that need a line above it? What you know right now is yes, it should have a line above it. Okay? I'm here to tell you. Yesterday, what's yesterday? We talked about congruency. We talked about congruency statements. Yes? And segment AB is congruent to segment CD. The lines are above and there was a congruency symbol. Well, what did I say when I put numbers in there? We don't always need a congruency symbol when there are numbers. Okay? So when we see numbers, there's an equal sign, and we don't put the line above it. Okay? Just because this comes back and it's written somewhere, and you're like, what in the world does that mean? If you were just to see this piece right here somewhere written, that means the distance from W to Y is equal to 7 inches. When they don't put a line above it, and they put an equal sign, that's the distance. Okay? So the distance of WY is equal to 7 inches. The distance of WZ is equal to 32 inches. What is the distance of YZ? So I gave you piece, and I gave you the total. Does everybody have a number now? You've done some math. What did you get, Jackson? 25 inches. Units matter. I try to put them. Okay? How did you do that?
I subtracted 7 inches.
Yeah, you try to subtract the total, the big thing, minus the piece. Okay, that's a segment addition postulate. We're not out in 2 minutes. No! No, that's not possible. Because we need to, we're going to finish really quick then. The last definition. What is the midpoint? The point in the middle. There's a definition if you turn the page that says it divides, the midpoint divides a segment into 2 congruent parts. If the distance from school to my house is 7 miles, what is the midpoint? 3.5, 3.5. So if I say it breaks it into 2 congruent parts, here's the beginning, here's the end, it breaks it right here into 2 congruent parts. Okay, it breaks it, we could also say it breaks it in half. Okay, so we just simply divided 7 by 2. Okay, but at this point, I'm supposed to say, what questions did you have in your homework? I'm going to assign a little bit more. We're almost out of time. So, I will answer more questions tomorrow. I will answer all questions tomorrow. See, this is what happened. It was midpoint. I gave them the definition. And then I gave them some homework. Okay, I need to talk to you about some homework. Put this homework. There's only like 6 more problems, 7 more problems from lesson 2 with lesson 1 homework on the same page. You can draw a line, you can skip down, you can turn it on the back. Lesson 2 homework. It's going to be numbers 13 through 21. On a completely separate sheet of paper that you will keep separate. You're going to start your postulates. If it's in the box, you can write it down. Okay? Postulates 1 through 4. 1 and 2 are from lesson 2. 3 and 4 are from lesson 3. Okay? Do you have any questions?
Madam Alden,
Yes.
I appreciate the Ferris Bueller reference.
Yes. Yeah. Didn't we watch that in the
Yeah.
Yes. All right, I gotta stop this.